We are live.
Oh boy.
Oh God.
Okay, so we're being recorded. Everyone remember being recorded? I will try to as well. Hi, everybody. I'm Daryl. Do we have, there's a couple of faces I don't recognize. Do we have any new members? Let's start right here. Catherine, unmute and tell us a little.
Hi, I'm a brand new member, so I just thought I'd come and kind of see what you all are all about. I've been going to the Garvey Observatory. I went a few weeks last month and got some wonderful tips and ideas and thoughts and really good instruction on using my telescope. And so I'm excited to be a new member, and Tim Thompson recruited me in. No, I mean, I just asked him about this, and he said, "Come on down." So thank you so much. I look forward to being part of the organization.
Did you not bring your telescope up to Mount Wilson too?
I did bring it up to Mount Wilson. I was a total newbie.
I thought I saw you up there. Thank you for doing that. As a total newbie, that's brave. Very, very good.
It was fun. It was a total blast. Love being up there.
Welcome, Catherine. Welcome.
Thank you. Thanks so much.
Welcome.
And all right, very good. Anybody else that's a new member?
I'm new.
Hi, how are you?
Hi, my name's Bill. I've also met some of you at Garvey. And just this week, I got the invitation to the group. So here I am. Really looking forward to learning and exploring with you all.
Bill.
Welcome, Bill.
Welcome.
Thank you.
Definitely welcome. Welcome aboard.
Bill, are you a visual guy?
I am a visual guy. Actually, I'm a beginning of everything guy. I tried to take a few photos of Jupiter and Saturn and some small DSOs, and yeah, everything's just beginning for me.
DSO.
Deep sky object.
Oh, yes, some nebula, some galaxies.
Great. Awesome. Welcome.
Thank you.
Okay, cool. I see somebody else. Preston, you're a new member, I believe. Yes.
Yeah. Hey, everybody. I'm really excited to be a part of the organization now. The name is Preston Dykes, and I'm an active astrophotographer. I try to go out every month and shoot under really dark skies, but I was really looking to up my observing game with my telescope. So I'm hoping to come out and learn from you guys and get some good tips. I work at JPL, and I produce the monthly sky watching video series that we do called What's Up. So I'm looking to get a little more, get my head a little more in the game and be part of this community.
So you remember who did it before you? What's her name?
Jane.
Jane.
Yes.
Jane was the first. Jane was the person that first let me look through a large telescope, and yeah. So
the Sidewalk Astronomers
we're founders of the Old Town Sidewalk Astronomers Monrovia, of which I'm part.
And they're still there.
Yeah. So welcome,
Preston. Still there.
Yeah, join us sometime.
So where in the dark? Where do you find dark skies?
Well, you have to drive 2 or 3 hours at least, right? So I go up to Inyo National Forest, Los Padres, out to Mojave, places like that.
Yep.
Well, you're in good company. We have a lot of guys that are doing exactly what you're doing. So you fell into the right place for sure.
Hope to make some new friends. Thanks.
Garvey is a good place to meet the real regulars of the club. So try and make it there if you can. Okay. That's a couple. Anybody else new here?
Hi, everyone. I don't know. Can you hear me?
Yes, absolutely.
Yeah. My name is Steve Gaffney. I just joined the club. Actually got accepted last week. I'm starting out, coming back into the hobby after many years of a break, kids and getting married and stuff tends to cut away your nighttime activities. But for right now, I'm a visual guy, but I'm doing a lot of research, reading a lot of books, and figuring out the best beginning to photography. I look forward to heading out to Garvey on Wednesdays to meet everyone, bring my scope because I have questions about it. Yeah, I'm just real excited to be a part of this community. Thank you for allowing me to join.
Well, thank you for being a member and being interested.
Welcome.
Garvey's going to be a great place for you.
Welcome.
Okay.
Looks like we had two more that's joined.
Hi,
New
yeah,
members.
this is Rick Gonzalez. I'm also a new member.
Hey, Rick.
Just recently joined. I'm actually part of the San Diego Astronomy Association, the SDAA. But I grew up in Monterey Park. My mother's house is right across the street from Barnes Park, so Garvey Ranch is really close. Grew up here for 33 years, but just like to expand in the astro community. I'm more of a astrophotography guy than visual, but I enjoy all aspects of it. And thanks for getting me in the group.
Welcome.
No problem.
Is that your image of M51?
Yes, that is correct.
Very good.
Well, welcome to the club.
Nice image.
Very nice.
Thank you. Thank you.
I think, is Vince, are you a new member as well? No?
It looks like Serene.
Is Serene on? Well, there she is.
My mic's off.
Shauna Do.
Hey, can you guys hear me okay?
Yes.
Yep,
And now.
coming through.
We can hear you.
Awesome. Thank you guys for letting me join. I'm super excited. I started this journey because of my son, who's 11, and I was able to share on my application how he was nonverbal. He's autistic, nonverbal at 3, but at 3.5, he decided to learn to read by watching NASA videos with closed caption. And the first thing he read to me was Supermassive Black Hole. So that's what started our journey on. So the reason I joined.
Awesome.
Great.
I had a nice
With him
conversation.
was
I had a nice
because,
conversation with Shauna.
Before
and,
him, I couldn't even tell you what planets, the planets in our solar system in order.
He's the next Hawking.
Yes. So, so I'm just sort of excited. He's actually asleep already. He had a really long day.
Well, he'll be able to watch this. This is
So
recorded
I'm
on
just super
YouTube.
excited to be able to share this with him and this be his thing that, you know, we
Awesome.
get to do.
That's great.
So this is being recorded
Okay.
and you can see it on the
Awesome.
YouTube channel
I'll
from
share it with him.
LAAS YouTube channel. And he can just
But
watch the whole
He
thing.
loves space, and I love watching him learn, and I learn along with him.
Well,
Well,
tell Nicholas I said hello.
Awesome.
All right.
I will. Thank you so much.
Okay. Is that it? Thank you all the new people for coming. Thank you very much. It's very nice to see new people come to the first meeting.
Daryl,
after they came.
Serene posted in the chat if you want to say hi to her.
Hi, Serene.
She's in a class right now.
Okay. Well, fantastic. All right. Well, welcome everyone. Welcome in. Welcome new members. Hello, everyone. You know, we have a lot of new members, and I'm really surprised at how many we are getting, and I'm not sure exactly what it all is about. It seems that our social media is working well. I think our outreach is working well. Our members are drawing in other members. It seems that now that we've come out of COVID and people are back out on just seeing other people, our members are seeing other people in various places, and they are so excited to get back out and do things with other people. I think it's been very contagious, and it's been working, and it's really great. So
Definitely.
thank you. I'm sorry, say again?
No, it was definitely, you know, people, because I'm seeing it across all my hobbies. They're so happy to be able to get out now that they're vaxxed.
his telephone will be pretty interesting too, because those
Is that somebody talking here? Oh, no, somebody's mic. Okay. All right. Well, I'm going to go through the committee reports rather quickly tonight. We have a lot to do. Spencer has a short presentation he wants to do about light pollution that we've been working on.
Good.
And I want to leave plenty of time for Tim's talk, and there's probably going to be a million questions. So I think what I'll do is just go through what we've had. I'll do the committee report. So Ford is first on the committee report, and we've had a nice star party there, and I believe that we have another one scheduled for October 1st. Is that right, Curtis? Is that still on?
Your mic's
Mic
off.
on. Okay, we have a public star party planned for October 1st at the North Lodge parking lot at Mountain High. We're gonna have that public star party. We're in the process of setting that up right now with the Mountain High ski area, and we're gonna run some articles in the newspapers. So, and we're gonna have some pretty good coverage up there. So I think we may have a pretty good coverage on that. We'd like to get probably at least a half a dozen or more telescopes up there. I think Joe and I'm going to talk to a couple other people and see if I can get some other people committed to go. But I know we got at least 2, but we'd like to see if we can get 6 or 8 telescopes up there for that star party.
All right, we'll put that information out. I think once people know that it's a good solid date, you don't think you have any problem getting people to come up.
Yeah, I think so too. I think it's going to be a good star party. A lot of people in the Wrightwood area are very happy about us doing this up there. So I think we're going to have a good turnout.
Great. All right, thanks.
Okay, thanks a lot, Daryl.
All right, so Garvey's next. I guess our Garvey director should take the first answer on Garvey. He is the director. Tim Thompson.
Well, I am the director, it's true. However, I was so busy last week, I couldn't get the confirmation of the reservation for the room yet for our Halloween Science Night on October 29th. Daryl's been working on that. But we've been doing well. We have a lot of loaner telescopes that Keith has been working on getting refurbished and ready to loan out. And I think the only details we have left are to figure out how to secure them so they actually come back one way or another. But most
we may have that problem fixed. We have a form set up that needs to be tested, but on a form site where people can go and put their deposit down there with PayPal or credit card. So that's in place. Most of the verbiage for the agreement is in place. So I think possibly this Wednesday, I'll be at Garvey, and I think, Keith, you're going to be able to be there Wednesday too?
I got a 50-50, but I'm shooting for it.
Okay, either way, no problem. If not, we'll pick it up next time. But I think we're about ready to go. We got the telescopes ready, we got the payment ready, and we got a bunch of trees out of the way and a lot more landscaping that happened at Garvey in the past few months due to a chance meeting with the Parks Department supervisor that I got along with really well. We hit it off, and he understood what we were doing. I took him a little walk and talk around Garvey, and since then, gosh, I don't know how to estimate how much better it is. But landscaping almost all the way around the dome area and all the way up to the museum, and more to come, and more to come in that area. So Garvey's doing well. Lockwood is also doing well. We've had a couple. I was up there 3 weeks ago on family night, and it was. I have to tell you, it was really nice. I don't get to Lockwood much because I'm almost always at Mount Wilson on dark sky nights. So I don't go the other way. I go to Mount Wilson. Everyone goes the other way. So I hadn't been there, I think, since before COVID, and it had been before COVID since I really saw the Milky Way. So it was really nice to be out there for that night. So awesome place to be. It's doing well. We have upgrades. The roll-off shed is coming along. The foundations are being built for that. It will be being reassembled. I don't know when, but it's getting there. Mount Wilson, Tim, again, I think we're very busy at Mount Wilson too. Go ahead.
Well, I know the date has been set already for the next public star party. I don't remember what it was. You might remember, or David might remember, but
24th. The 24th.
What was that?
The 24th.
The
24th. Okay. So it'll be run just like the previous public star party. Otherwise, I think all our 60-inch nights are booked and ready to go. If you haven't signed up for a 60-inch night, Daryl is the man. He's down there on my screen. Daryl is the man.
We have 60-inch nights in November is the only night left that has open spots. Everything else is booked. The 24th, the same night that we're having the public star party in the parking lot, there is also our 100-inch night that night. And there's probably something in the 60 as well. So it'll be another very busy night at the front gate. We will be handling that a little bit different this time possibly, but should be good. The last star party went off really well. And LAIS is also helping out and backing up Mount Wilson at the lecture. Did that already happen, or is that next week?
That's this
17th.
coming weekend.
That's this Saturday, right?
This Saturday.
This Saturday.
So LAIS, I don't know how many people know, but what we do with them is when they're having an event and having a lecture and open telescopes, that people get to go to the lecture and then they get to do viewing. But there's too many people. The auditorium holds, I think, maybe 200, which is too many people to go see the telescopes all at once. So LAIS comes up with 4, 5, 6, 8 telescopes, whoever shows up. We set up telescopes outside so that people can show them stuff while they're waiting to go in and look through the 100-inch. So it's a blast. It's a good support for them, and we get reciprocal perks on our end as well. Okay, so
They're filled up this Saturday for scopes already. I understand. They're already filled up to the max.
Okay, and how many is that? How many do we do? How many do we commit to? Approximate.
Oh, Evan knows the exact number. I
think. Is it like 6 or 15?
I think it was 6 or something like that.
Okay, so closer to 6. All right, that's fine.
Yeah.
All right, cool. All right. Griffith is always is up in the air. We have no official star parties, I don't think, that are announced. We've had a couple of unofficial star parties that weren't announced that went well. Griffiths asked us to bring up a certain, what did we get, like 6 people, 5 or 6 people?
We got more than that. They wanted 12. They must have got 12 at the last star party. I'm pretty sure that Mark Pine has dates on his calendar and has told the employees to be ready on those dates, but he hasn't said anything to us or to me or to you.
But we have insiders. We have inside people.
Yeah.
How is parking handled for the observers to bring telescopes up?
You get a certificate and emailed to put in your dashboard. They let you through.
Okay, just that lot that's closest to the.
Yep.
And the staff provides carts to shuttle back and forth your gear from the parking. It's super, super great. It's one of the greatest perks.
Great, thank you.
So if you're bringing equipment, you drive right up to the circle and you unload there, and you have people to help you unload in carts, and then they watch your stuff, and you go back and park in the parking lot and come back.
Perfect, thank you.
That's how that works. All right. Okay. Well, that's pretty much it. All right, well, let's have Spencer talk about the Dark Sky initiative and what's going on with that, and do a small presentation, and then I'll introduce Tim. Unless there's any questions right now before we go to this. No questions? Okay. All right.
All right, hang on. I'm going to share a screen here. I've got a couple of slides I just want to quickly go through. Just 1 second. Okay, let's see. Here we go. All right, so basically, we've kicked off a effort to reduce light pollution several months ago, and towards that end, we started a petition on change.org, and I'll get into that in just a little bit. But we're handling this on several fronts. So we did the petition change.org, and we naively thought, okay, well, we get enough signatures on the petition presented to the Board of Supervisors, and we'll get some traction on it, at least get an audience with them. But we've run into all sorts of roadblocks, and they basically, their staff is pretty adamant about referring us to the LA County Planning Department for enforcement. So we had to step back a little bit and be a little less ambitious, and we actually managed to get in contact with one of their planners, and we've been working with her. And so basically, and one of the things that we did on just a long shot was invited them to join us at our September 17th family night. And to my surprise, they accepted. So not only is the planner that we've been working with coming, but her director is coming, the person who wrote the Dark Sky Ordinance is coming, a couple of other people. So I plan on being there. I know Daryl's planning on being there. And so if any of you are planning on being at the September 17th family night, or just thinking about it, please try to attend. I think the more people we have, the better. The whole idea behind that is just to show them what dark skies look like. Now, Lockwood is not the darkest of dark skies, but it's much better than downtown LA. I think for them to see the contrast and to see the Milky Way without even having to try is going to help in our favor. The main thing that they want us to do is they want us to focus on education and awareness. And so one of the things towards that end is that turns out a lot of people are not aware that there is a dark sky ordinance. And so let me back up a minute. So the dark sky ordinance is basically applies to the unincorporated parts of LA County. So places like Pasadena, it does not apply, but any of the unincorporated areas, the ordinance has been in effect for about 10 years. 10 or 11 years, and it has not been very effective. And part of it has to do with, when we talked with their planner, she said, well, people have been asking us if we have a dark sky ordinance. And so that she says that tells us that we're not very good at distributing information about it. But the part that I want to bring up here is that they also, the enforcement is basically complaint driven. They're not going to drive around looking for non-compliant lighting in the unincorporated areas. They depend on people to report it. So number one, so my ask of the membership, and we'll try and send out an email to everybody too, is if you live in an unincorporated part of LA County, and you're driving around at night and you see an unshielded light, report it. Take a picture of it, get the address, the time, and report it, and turn it into them. The URL for the reporting is on the screen here. And that's number one. Secondly, the light should not be on all night. They're supposed to be on a timer or a motion detector. So those are the two easiest violations or non-conforming parts that we can sort of take care of. And I think our thought is that the more pressure they get in terms of just the more complaints that come in, the more likely they're going to be paying attention to the dark sky ordinance. The second thing that we're doing is we have a request in the State Senator Portantino's office to sponsor statewide dark sky friendly legislation. So the idea is that states like New Mexico, for example, they have a statewide dark sky ordinance that basically mandates that every county or every city have their own dark sky ordinance. And so it sets minimum standards for those local ordinances. And so that's sorely lacking in California. I think there are about 17 or 20 states that have dark sky friendly legislation. And so a request into Portantino's office is for him to sponsor that. The bad thing is that he's just announced that he's not going to be running for office again. So we're going to try and get this through quickly. their cycle was that they're out of session now, and so now they're entertaining proposals for new legislation, and so we're hopefully get on the docket for that. And the last thing I just wanted to add is that our dark sky petitions now is 1,502 signatures. There's a URL at the bottom. If you haven't signed it, please take a few minutes just to go log in and sign it. And the whole idea is that the more signatures we get on this, the more weight we're going to have when we talk to people about it. And also, once you hit certain thresholds, then the news media will start picking up on it, and hopefully we'll get some more traction that way. But it's going to be a long effort, but I think it's going to be well worth it. The goal right now is just to actually not to stop the spread of light pollution. I'm not even going to try and push it back to where it was in 2011 when the ordinance was passed, but at least we want to sort of have a plateau. I didn't have time to pull up the drawing, but and I can share it later, and I'll probably share it in the email I send out to the membership. But using satellite imaging, you can actually see an increase in light pollution from when the dark sky ordinance was enacted to now. And so instead of having that keep rising, I'd like to at least to have that plateau off. So that's the update. Last thing is, if anybody wants to join us, we could use some help on our committee. There were 3 of us, now we're down to 2. So anybody who would like to join, please let me know.
Spencer's been doing a lot of work in the background. He's being very humble about this, but this stuff is hard to do, hard to write really good letters to these people that respond. And so we're taking the opportunity. I'll be at Lockwood on the 17th as well to meet these people and see, because these are the people who can make a difference, who can make some changes. So if we have their ear and they see what we're seeing, we have a good chance of having things go up, maybe not spectacularly, but at least they'll know. They'll push in the right direction. We'll be going in the right direction. So everyone go, if you lost the URL is also on our landing page on our website, laas.org. You can click the dark sky survey there as well.
Right.
The petition. Something else?
Steve Gaffney had a question. Steve Gaffney had a question. It says,
yes,
can you please explain? It says, can you please explain what unshielded light is?
So basically,
bare bulbs.
Well, there should be a cover that extends out so the light is directed downwards and not just broadcast all over. So a bare bulb is the worst case. The worst is the at one end of the spectrum. The other end of the spectrum would be sort of like a can light, where the bulb is recessed into the container and directs the light down. Now you do get some lighting reflecting off the ground and back up into the sky, but at least the bulk of it is directed down and not just broadcast in all directions.
Are these civil lighting, city lighting, or is it just any lights?
The dark sky ordinance applies to both residential and commercial developments.
Okay, thank you.
Question.
But, yeah, go ahead.
Would it be possible after this group of people go up to the SKAS, would it be possible to have them go up to Mount Wilson to see what, hey, this you could used to see the Milky Way from here, and this is what we've lost.
It's a very good idea, and I will be probably bringing that up to them on that night.
Yeah.
And one of the things I like to point out with light pollution is when you look down from Mount Wilson at the city lights, every light you see that's a direct light, not a reflection off a street, is wasted energy, expensive. It's light that's not going in the direction that you want it. And it's very pretty, but it's completely wasted energy for any light that is not shielded such that the light goes down, as opposed to up to Mount Wilson from the LA Valley.
So everyone go home, look for any lights that are up, turn them down so Mount Wilson gets darker. Thank you.
So speaking of reflections off the street, there's a new push in the city to pave over the asphalt streets with like it's like a light gray reflective. It's for the thermal. But I looked at that and I said, wow, all that light coming down is going to hit that and go back up.
Another problem that we'll tackle another time.
Okay.
Let me just take 1 second and share one screen. This is very informative. This is very informative. I found the email.
Just the light overlay?
Yeah. So this is, you see the three figures?
Yeah.
This is satellite imagery. So basically this is showing the light pollution or the light at night. And so we picked Lake Los Angeles, right in the middle of nowhere, right? So that's clearly an uninhabited or very sparsely populated area. And if you look down here, you can see where the light radiance has increased. The ordinance was passed in 2011. So you see this red dotted line? That's where we are right now. So it just keeps going up and up and up. And so I'd like to bend that curve and flatten it out at some point. And ideally make it have a negative slope, but that's going to take years.
It's a light pandemic. Think of it as a light pandemic. We gotta turn that curve back down.
Right.
Okay.
Okay. Thank you.
All right. So everyone get on board with that. If you just as a show of hands or something, how many people live in an unincorporated area that happen to be here tonight? 1?
Okay.
2, 3?
Okay, so Teresa, I guess you guys don't count. This is LA County, but the Kern County has its own light pollution ordinance. But the other thing is that you don't necessarily have to live in the unincorporated area. If you are working or driving through an unincorporated area and you see non-conforming lights, just take a minute, take a picture, note the time, and
so you do not have to be a resident.
Yeah, in the unincorporated area.
Okay.
They're complaint driven, and our goal right now is to generate a lot of complaints so they realize, oh my gosh, there is the problem that we have to address.
Good. Okay. All right. Well, if there are no questions, I will.
Daryl, real quick.
Yes.
I live next to Sherman Oaks Park, and I think there's some unshielded lights down there. So that's not unincorporated. Could I also generate a complaint on that?
You could probably generate, well, it would not go to the Sherman Oaks. Is that the city of LA?
Yeah.
So the city of LA is, you'd have to deal with them.
Okay.
But it would not hurt to generate a complaint to them, although the dark sky ordinances have some provisions for prisons and parks and other areas are, they're sort of exempt.
Oh.
But you could, but if there's enough interest, they may pay attention to it. City of LA is something that we, a long time ago, one of our members was trying to tackle it for the city of LA, and she didn't get very far. But that's not to say that we shouldn't try again.
I've written them, I think, 3 letters now.
Yeah. Well,
thanks to those efforts, I think that we'll start at the outskirts where we can actually do something and see what happens from there.
Yeah. Oh, the other thing that we're trying to do is that people have heard the phrase urban wilderness interface. So cities like Altadena, La Cañada, parts of Castaic. So those are areas that border a wilderness area. And so it would be, one of the planners said that we could probably get a lot of traction if we got some sort of legislation or some ordinance sponsored to address that urban wildlife interface. Because there you have to, basically it's a grassroots effort. You're gonna have to talk with the local city councils and whatnot, or governing city governance committees to get traction there. Okay, well, if anyone gets really interested in helping out, certainly contact Spencer. Groups.io or the website. I think you can contact us from multiple places. Yeah, just shoot an email to secretary@laas.org. No. There you go. Okay. Do we put the raffle in the chat? No, I will do that while you're introducing the speaker. Okay. So we'll put that. So Spencer's going to put the link for the door prizes in the chat. So everyone go to the chat and sign up, and we'll do that a little bit later. So let me introduce our speaker, who's going to give us a James Webb Telescope update, because he has done a talk on this, but a lot's happened since that talk. Spencer, can you put up Tim's Yeah, hang on one second. Let me pull that up.
Extensive stuff that
Figured
he's
out who I
done.
am yet, huh?
Yeah, most people know. You know, there's so many things that Tim has done. Has been president of the club, JPL, astronomer, astrophysicist, chess player, chess teacher. You know, there's so many things that Tim does. I'm glad to know him. He will be, I think, donning his Ask a Scientist robe at the Halloween party. Is that correct? Are you going to be in your robe and hat?
That's right. So if you want to see me in my wizard's outfit, you got to come to the Halloween science night.
And you have a new staff, is that correct?
That's right. I have the staff of wisdom.
All right. Okay. You can all read what Tim does. There's all kinds of stuff. Can leave that up. What's the biggest one here? So I think, you know, the one that he relies on most when he falls back and he's having problems is that BS degree.
Yeah.
All right, Tim, take it away, man. Tell us all about the update on the James Webb. We're all excited, I'm sure. Thank you. And anyone who's not doesn't need to speak, you should be. Looks like everyone's muted anyway, except me. All right.
I do need to be able to share my screen.
Okay, sorry
Spencer,
about that.
Unshare.
Okay, there you go.
Oh boy. Now let's see.
I don't know, but
voila.
Perfect.
Well, can you all see my rendition of the James Webb Star Destroyer?
Yes.
I've never been able to get over the similarity between JWST and a Star Destroyer. Sorry, but it's just, that's the way it is. My mind works that way. So, okay, the first talk I gave, the last talk before it launched. It's kind of hard to talk about a space telescope before it launches because it's nothing to talk about except it's going to do this or whatever. So, you know, it launched last Christmas. It's the only space telescope named after an administrator, not an astronomer or a scientist. It probably explains why it's billions of dollars over budget and decades behind schedule. But in any case, it finally did launch. The most interesting thing about it, about that aspect of it, was I realized that James Webb Space Telescope weighs about 55% of what the Hubble Space Telescope weighs. Despite the fact that it's somewhat bigger than the HST, it weighs less. So that tells you something about the advances in telescope making technology between now and then. So I'm not going to talk about the telescope itself a little bit because it did all that the first time and we don't have time to go through all that again. But here, of course, is what it looks like. And assuming my little cursor is actually visible to you, the big gold thing in the middle, of course, that's the 18-segment primary mirror. And under it is the 5 layers of the solar shield. The computers and everything are on the bottom. And it really is pink on the bottom because of silicon doping in the sun shield material. So when you launch any spacecraft with telescopes, instruments, whatever, it goes through a commissioning phase. So the first thing that has to be done is spend months getting the instruments down to temperature, making sure they all work, everything works great. So in the end, what commissioning discovered was that virtually everything about the JWST works much better than it was expected to work. They even point out that the mirror segments are cleaner than they expected, which means less scattered light, better throughput. The mirror is better aligned. The detectors work great. Everything works great. And because of efficiencies in managing fuel for mid-course corrections and the like on its way out to the Lagrange 2 point, I believe it is, there's enough propellant on board to last for 20 years. 10 years was the expectation and the requirement before launch. They say they'll have enough for 20, which is good, because with the era of great big huge 30-meter class telescopes starting in a few years on the ground, you want to be able to have follow-up with some of those big telescopes from the ground on things that JWST discovered in space. So the bottom line is the commissioning went really, really well. I do want to mention something about the mirror, mainly that we all have telescopes with one mirror. And those of you who have aligned your mirrors, knowing that if you really know what you're doing, okay, you can do it without too much trouble. But if you don't, aligning your own mirror can be a pain in the neck. So when you launch JWST, all 18 of the mirror segments have to be locked down, stabilized. They don't shake all over the place during launch. Then you have to let them loose and find out where they're pointing. When they point at the first star, they see 18 images like this. You want one mirror, not 18 mirrors. So you wiggle each one of those segments till you figure out which one of those dots goes with which segment. You can see that here on the screen that they've been labeled. And finally, you have to tweak those segments around so that all those 18 things become one thing. And that's not easy. That took quite a while to do. There's lots of fine tuning on the mirror segments. But as the commissioning phase demonstrated, the mirror alignment is even better than it was anticipated to be, which gives you, slightly better data all the way through. So that worked great. You've probably heard that a micrometeorite hit the spacecraft. Well, this, of course, happens to everything. And in fact, when the commissioning report was written in July, JWST had already experienced 19 micrometeoroid impacts. 6 of them were on the mirror. 5 of them were basically unnoticeable, but 1 was unexpectedly large. That made the news for a while. The mirror segment you can see on this diagram is partially blocked by one of the supports for the secondary mirror. So one of the ways of judging the value of your optical system is what's called the Rms Wavefront Error. RMS is a fancy acronym for root mean square, which is a statistical thing we won't get into now, but it's basically an average, a statistical average of the wavefront error, meaning that your detector expects to see light waves arrive from the mirror in a specific pattern. It won't ever get exactly that pattern because of scattering and other errors and uncertainties in the optical system. But this impact added 59 nanometers of RMS wavefront error, for those of you who are optics people, to that one of 18 segments, and that turns into about 5 to 10 nanometers for the entire system. And since the RMS error budget for the entire system is around 180 nanometers RMS, it basically is not important, even though it looks on the interferometric image like it's a big deal, sounded like it was a big deal in the news. It really isn't. It hasn't done anything to the telescope that we can't work around the old-fashioned way. And I do want to remind you what the instruments are and what their capabilities are. There's a lot of imaging and spectroscopic capabilities between 0.6 and 5 microns, observing wavelengths. And the mid-infrared instrument actually works from 5 to 28 microns. And that's that long wavelength that's going to allow you to see really high redshift sources and be able to probe a lot of other science nearby. So you can see it has continuous imaging and spectroscopic capabilities all the way from 0.6 to 28 microns. So you must remember that eyeball visible light comes to a screeching halt about 0.7 microns, which means very little of what comes out of the James Webb Space Telescope will be light that you can actually see. It's all infrared. So the colors you see on all of the James Webb Space Telescope images are fake. in the sense that if you looked at the object with your eyeball, you would see nothing at all because your eye is not sensitive to that wavelength. So remember, you're not going to see any true color images the way you did from the Hubble. They're all going to be color paletted to understand an invisible infrared image. And so let's look at some of the science that has come out of the telescope. I want to remind you what the science goals were for the mission: the formation of the first stars and galaxies, studying the evolution of galaxies, star formation, stellar evolution, extrasolar planets. You won't find the solar system there, but you will see later on that the James Webb Space Telescope could do some interesting stuff in the solar system. What usually happens is you launch a telescope with a plan, and then you observe something and your plan goes out the window because that's really fascinating. You got to go look at that, and it's not part of the plan. And that may happen. It hasn't happened yet, but that may happen. Before I go into this, I want to remind you what a redshift actually is. And what you're looking at here is modeled spectra over on the left, and you'll notice several large vertical spikes. What's plotted in a spectrum is wavelength along the horizontal axis and brightness vertically. And so those bright spikes that stick well up are called emission spikes, and they are recognizable. You can identify them with some element you know, or some feature that you're aware of, and you know what wavelength it would have in a laboratory. When you observe it, it's going to show up at a wavelength farther into the red than you would have expected to see it. The difference between those is the red shift. And in our modern expanding universe, Big Bang cosmology, the red shift correlates to a distance. And so here they're demonstrating redshift 10, 11, and 12 spectra, and they're giving you the age of the universe at the time that you see this object and how far away it is, and what's called light travel time distance, meaning how long did it take the light to get to you from that source. And as you can see, when you get into redshifts above 10, we're getting pretty close to the Big Bang, getting under a billion years after it. Redshift 10, maybe 11 is as far as the Hubble Space Telescope can see. The plan is for JWST to see to a redshift of 20. John Mather, the chief scientist, says it will do 30. We'll find out. But most of the redshifts we're going to get actually are not spectroscopic redshifts, which is what you really want. They're very precise. Most of what you get is something called a photometric redshift, because what we have is an instrument that looks with broadband cameras, broadband photometric equipment. So you know, for instance, in this diagram, you have the integrated brightness of the blue band, the V band, the I band was near infrared, and Fricker made this diagram, didn't explain what it was. I steal my diagrams from the web like all good speakers, and so I don't always know everything. The black line through the middle is a model spectrum. So that's what the real spectrum looks like, but you don't get to see that. You only get to see the red, orange, and the blue. And then you have to pretend you know what the spectrum looks like. So when I look at this animated GIF, as the spikes go through the filters, you can see the brightness changing. The redshift is given up on the top. And this spectrum, when it moves into view on the left, you will see a very sharp downward cliff at the left end of the spectrum as it moves into view. There we go. That's called a Lyman break, and the galaxy spectrum that has that is called the Lyman break galaxy. And as that break moves through the blue band, you'll notice it just disappears and you don't see it anymore. And likewise, the V band, it will disappear and you won't see it anymore. And when you see this happen on your photometry, you now have a candidate for something that could be a very high redshift object, but you need to go and look at the spectrum in more detail to avoid being fooled. The bottom line is that a spectroscopic redshift is not going to fool you, but a photometric redshift can, and that will become important later on. So the first thing I want to look at is extragalactic cosmology. And this image you probably have seen. This was the very first image to come out of the telescope, labeled as the first deep field image for James Webb. NIRCam over on the right is doing short wavelength infrared. MIRI on the left is longer wavelength. The color code is at the bottom of the image. Naturally, it's color coded so that you're trying to read blue, purple letters on a black background, which is a little on the hard side to do. But since the colors are all basically fake, the channels for most of these images have been assigned so that the color progression matches what you would expect from eyeball color, so that the short wavelengths are blue, the long wavelengths are red, and the ones in the middle are yellow-green, so that at least the progression, the things that are visible at longer wavelengths predominantly look red-orange, and the things that are visible at short wavelengths predominantly for that instrument look blue. And it's really the image on the right that we want to look at because it's easier to see what's going on here. You notice that there are a number of stretched out images of background galaxies, and this is gravitational lensing at work. There are many famous images from the Hubble Space Telescope that do this. Imagine that you replace the gravitational field of the foreground galaxy cluster with a really bad lens that's got lots of deformations in it, and the light comes through that lens. It's going to deform everything, stretch it out, bend it, and that's what the mottled gravitational field is doing. As you remember, relativity teaches us that light travels along a curved arc through a gravitational field, but the field is not smooth and continuous throughout. It's knotty, it's bumpy, so it creates deformations and multiple images of the same object. We know, for instance, that if you see my cursor, these two images are the same galaxy, and it's quite likely that these two are also the same galaxy. And you may see 3 or 4 or 5 images of the same galaxy in an image like this. But aside from distorting, this also magnifies so that objects which would under normal circumstances be too dim for JWST or any other telescope to see will show up because they've been magnified. And the magnification factor can be in the thousands, make things thousands of times brighter than they would otherwise be. So these, when you look at an image like this is what people like to see. They like to see obvious galaxies, something unusual. What cosmologists like to see are little splotches, just a little dot that looks totally boring to the non-scientist. But these are the things that are very far away, high redshift objects that might be galaxies. And in this case, in that field, we see 4 galaxies. I've put the redshifts over on the right because they weren't given in the original diagram, just the light travel time distances from 11.3 to 13.1 billion years. And here's an example of what I was talking about before. There are features in the spectrum that we can identify with hydrogen and oxygen. And as those features show up at wavelengths farther to the right, longer wavelengths, that's the redshift, and that's what you derive the distance from. And here is an example of getting the chemical composition of this highest redshift object. If you can remember my earlier talks, I have mentioned that if you freeze the expansion of the universe and pace off the distance between us and another object, the real physical distance is extremely large compared to the light travel time distance. So when they say this galaxy is 13.1 billion light years away, it means it took the light 13.1 billion years to get from there to you. But during those 13 billion years, the universe has been constantly expanding. So if you freeze the universe now and walk from here to that galaxy, it's over 30 billion light years away, not 13. So distance is kind of a dodgy concept in cosmology, and you have to be careful to tell people what distance you're using. The light travel time distance is the one you always get from every web page, book, explanation, almost everybody. If they don't say explicitly that it's some other distance, that's what it is. Now here, you could use all these lines to get the redshift, and indeed that's more efficient than using just one emission line. You use 2 or 3 or 4 or 5, you get better statistics. Each one's going to have some uncertainty and a more certain redshift. But in this case, you're also getting the chemical composition of the galaxy. And the chemical composition comes from stars and stellar evolution. Here you can see hydrogen, which is all over the place, oxygen, and neon. A relatively low mass star like the sun can generate oxygen, and it will wind up, most of it, trapped in a carbon oxygen white dwarf that the sun leaves behind when it creates a planetary nebula. But a lot of the oxygen that came with the sun and a lot of the oxygen made in creating the white dwarf will go into that planetary nebula. Neon, not so. You need massive stars and supernova explosions to make neon. So if you can get the relative abundances of, say, oxygen and neon and multiple other elements from the spectra, you can say something about the stellar population in the galaxy. For instance, you might be able to figure out the stellar mass using this kind of information and the color that you see from the galaxy. So this is valuable information. One other thing I wanted to mention that I had not talked about before is from the NIRSpec instrument, the Near Infrared Spectrometer, which has a really, really spiffy device attached to it. On the ground, when you're looking at a crowded chunk of sky and you want to take multiple spectra at once, you create in your machine shop a mask that you put over the telescope that has a little hole in it that perfectly matches the location where you know that a galaxy or whatever other object you want to look at will be. So that the only light you get comes from those objects. And you put a fiber optic on each one of those holes, and you feed the fiber optic into an integral field spectrometer or some other device, and you can get 40, 50, 100 spectra all at the same time, depending on how your instrument is built. You can't do that with a space telescope. So in this case, NIRSpec has a mask that's placed over it that has approximately 250,000 individually controllable micro shutters that measure about 100 by 200 micrometers. How they do that, I don't know. I'm not into the nano engineering business, but this looks like a pretty good trick to me. A typical plucked hair off your head, if there's a typical hair, is about 100 microns in diameter. So if you pluck a couple of hairs off your head and bunch them together and look at the ends facing you, that's 100 by 200 micrometers. That's how small these little shutters are. There's 250,000 of them. So they can open and close them at will, depending on what objects they want to look at in their field, which they will know in advance by having imaged the field first. I'm a big fan of this technology. But I want to zoom in on this, the MIRI image. This is the long wavelength, in particular 7.7 micron. And look and see, well, what do you get out of an image like this other than the pretty picture of the near cam image, the magnification, the gravitationally lensed sources? What's actually in this image? Well, the bottom line, and I'll show you some of the data, is that we've discovered a great deal of sources, a lot of interesting sources buried in this image. And the conclusion is that the 7.7 micron observations from MIRI are going to be perhaps more informative than was originally thought. Now, this is a histogram counting up the sources found in that image. There are 362 sources, and they have to be detectable both in the 7.7 micron and 3.6 micron filters at at short distances for things that are fairly nearby. 3.6 microns will be dominated by starlight. 7.7 microns will be dominated by warm dust. But as you go to higher and higher redshifts, you're seeing shorter wavelengths that have been redshifted into your view, and 7.7 microns becomes increasingly dominated by starlight, and that's going to become fairly important. You're looking at the apparent magnitude plotted along the horizontal axis and a count. It's a histogram, so it's just a count of sources up the vertical axis. And as you go up in magnitude, as things get dimmer, you're seeing more and more sources because you're looking farther and farther away. Remember, you're looking at magnitude, so all the distances are clumped together here. You don't know how far away any of these things are yet, you just know how dim they are. It's always going to be more and more dim sources that are far away. And that keeps going up until you get to about magnitude 25, and then the right side of the plot just drops off. And there you're running into the sensitivity limit of the instrument. So between the low magnitude, say 19 up to about 25, you have enough information that you can make scientific judgments about this population. But once you go beyond 25th magnitude, that doesn't work. Now, there's a whole lot of data plotted in this paper and a lot of studies, but I just want to look at one set. This is photometric redshift along the horizontal axis, and I have added in the GLY, means gigalight years, just billions of light years. That's the light travel time distance that you would normally expect to see associated with that redshift. So the objects out at redshift 7, they're nearly 13 billion light years away in travel time distance. Over on the left, you're looking at the redshift distribution of the 7.7 micron sources. The gray bar at about redshift 0.3, the little gray line that sticks up, and the very tall blue bar represent the foreground cluster that's doing the gravitational lensing. That's SMACS 0723. And it's fairly close by it. So that's like 4.02 or 4.2, I think it's 4.2 billion light years away in light travel time distance. And so everything closer than that, the two little bars on the left are foreground objects, and then the background objects going into higher and higher redshift or over towards the right. And as you can see, there are some fairly high redshift sources in this image, 5, 6, and 7, which are pretty good redshifts. Clearly, they've been magnified by the gravitational lensing magnification that I mentioned before in order to be able to be visible. Really interesting is the plot on the right, which is a logarithmic plot of mass, basically. So what you're looking at on the vertical axis is the logarithm, meaning the power of 10, for the stellar mass of the object is plotted. So 10 means 10 to the 10th or 10 billion solar masses, and 11 is 100 billion solar masses, and so on. It's scaled in solar masses, which is typical in any astrophysical cosmological affair. And again, the distance given to you in light travel time distance. Now you'll notice that as you go far out in redshift beyond 6 and 7, there are some pretty massive objects. And we're getting to where we're maybe less than 1 billion years after the Big Bang, making some massive galaxies. And that's going to be a problem. And in particular, an interesting source is this one. Now we only have the photometric redshift for it, but it looks pretty good. You can see, as I had in the demonstration of the photometric redshift, where there was a sharp drop off in the spectrum, you see that here, right around the observed wavelength 10 to the 0, which is 1 micron, so that the bands to the left are invisible. You have no brightness there. And then 2 bands around the break, and then several bands along the curve. This gives us a photometric redshift of 6.86. At that point, the universe is 790 million years old. So you're looking at a universe as it was 790 million years after the Big Bang. Well, 2 times 10 to the 11 solar masses, which is the stellar mass, no dark matter, dust, or anything else. It's the stellar mass that you get from the light and the colors that come from the galaxy. That's 200 billion solar masses. That's roughly the same as the stellar mass of the Milky Way, which means this is not a small dwarf galaxy. It's a really big galaxy. And the images on the bottom are intended to show you that the galaxy is well detected at both wavelengths, so we know what we're looking at. It's not an incredibly dim, mysterious thing. We have a good handle on it. It's bright, has a good signal to noise. It's hard to come up with a model to create a galaxy this big, this massive, that soon after the Big Bang. And this leads us to what is the real story behind the James Webb Space Telescope, which you've probably seen because it's all over the internet. Everyone has repeated it on multiple occasions, that the James Webb Space Telescope has proven that Big Bang cosmology is wrong, and evolutionists are picked over the James Webb Telescope images, and we're all running around pulling our hairs out because it has destroyed all of our faith in physics and cosmology. Take it from me, that probably has not actually happened. Don't worry about JWST disproving Big Bang cosmology as yet. However, there are some interesting things to be seen in the James Webb Space Telescope, and one of them in another field, not the same galaxy cluster we saw before, is something they have dubbed Schrodinger's galaxy. The kind of problem you see here with this object is not new. There are many cases of this in cosmology, but we have to make up nice, snazzy one-liners so we can get headlines and attract attention. So the reason they call it Schrodinger's galaxy is because it can be in 2 places at the same time, because it has 2 different possible photometric redshifts. The images you see on top show you that a little smudge, and on the 2 100, 115, 1.15, and 1.5 micron filters, it's invisible. So this is one of those dropout galaxies where the 2 bands to the left, if you will, of the Lyman break are gone, and then you begin to see it at 2 microns, and it gets brighter as you go up. Well, it looks like it has a redshift of nearly 17, which is way beyond any other redshift anybody. The The current record holder is around redshift 11, but James Webb has already uncovered a host of possible redshift 12, 13, 14, 15 galaxies. And this one is one of the longest redshifts, about 17, which would look at a universe as it was 220 million years after the Big Bang. And from its colors, it appears to have a fairly high mass, basically 5 billion solar masses, which is comparable to the small Magellanic Cloud in our own local group of galaxies. But there's a problem. Now, what you're looking at here, flux density is just brightness. So on the two plots on the left, the vertical axis is brightness. Again, it's logarithmic. 10 squared is 100, 10 to the 1 is 10. And a probability measure, which always goes from 0 to 1 on the vertical axis of the plots on the right. Now, on the left, you're seeing two spectra. One of them, the orange line, is a Lyman break galaxy, high redshift galaxy, with a redshift nearly 70, it's about 16.6. And the other gray spectrum is one for a quiescent galaxy, which means a galaxy that's not forming stars at any particularly fantastic rate. The Milky Way is kind of a quiescent galaxy, but there are those that are more quiescent. And the photometric redshift, the photometric points, are the red dots with the error bars, vertical error bars on them that I'm putting my little cursor around. These are the data that you actually have, and these two orange and gray spectra are model spectra. You have some data here and some data here, and these bands are all invisible. It turns out that if your photometry noise level is small, then the probability is that this is a redshift 17 galaxy. And if you look at the top plot on the right, that's what you're seeing, redshift probability. And there are two things, one called EZ and one called Prospector, which are just two different software packages that, given the photometry, will compute a photometric redshift for you. And according to these results, you have a solid guess at a nearly redshift 17 galaxy. However, if you bump the noise floor for the photometry up, if you don't know really how precise your photometry is yet, and that's a thing they're working on, then your point down here just to the left of the Lyman break gives you a very small probability. Now there are two bumps on the bottom plot to the right, a little bump around 5 and the big bumps around 15 or 16. So there is a small probability that you're actually looking at a redshift 5 interloper. That's not a high redshift galaxy, not as high as you think, but it's a different kind of galaxy, one that's full of dust and a lot of star formation, and the dust will mask a lot of the starlight and give you the probability of a redshift 5, or one that has quenched and is not forming stars. So this, when they call it Schrodinger's galaxies and talk about it being in two places at once, they mean it could be nearby, could be really far away. It's probably very far away. But until we look at it with a spectrometer and get a spectral redshift, which will solve the dilemma immediately and permanently, we really don't know how far away it is. And this is an example of the problem I talked about when you have photometric redshifts fooling you. This could be a case where we're being fooled by the photometric redshift, even if the probability is high. So when you see the redshifts and distances from these galaxies, don't just jump on it and assume, oh yeah, it's got to be billions and billions and billions of light years away. Might not be. If it's not a spectroscopic redshift, you need to know which one you've got. Evidence in favor of it being at a redshift 5. Here's the image, and the black spot in the image on the left is that little galaxy that we were looking at. It is surrounded by a bunch of galaxies, all of which are pretty clearly redshift 5 galaxies. So it could be part of a cluster of galaxies that's at a redshift 5. The plot on the upper right, the dark solid line is a histogram of the redshift for all the objects within 30 arc seconds from our galaxy. And the blue dashed line is all of them in the entire CERS Webb database. And you'll notice that the solid blue line has a bump in it, which the other one doesn't. That's the local galaxy cluster. And it coincides with the probability curve in orange for the redshift 5 of our galaxy over in the middle. So the environment implies that we're being fooled and it's actually a redshift 5 galaxy. But of course, it could be a very high redshift 17 galaxy that happens to share the same line of sight with this galaxy cluster way off in the background. So in fact, we don't know where it is for sure. You need a spectroscopic redshift. But the fun part is, suppose that actually is a redshift 17 galaxy. Now we've really challenged the galaxy evolution people to come up with a model that will produce a 5 billion solar mass galaxy only 220 million years after the Big Bang. By our standards, it's a dwarf, like the Small Magellanic Cloud. But doing even something that small in only 220 million years is a problem, and it's going to be a problem. However, suppose it's actually a redshift 5 galaxy, it's dusty, and it's star bursting, which means it's forming a lot of stars, but they're embedded in the dust. We see the thermal emission from the dust. Now we've challenged our galaxy evolution models again, because you have to make dust by stars. Stars evolve through a generation, and that makes dust, and then another generation that makes more dust, and so on. You need many generations of stars or a very high star formation rate to generate enough dust for the galaxy to look dusty. And in a redshift 5, it's not 220 million years, it's more like 700, 800 million years. It's still less than 1 billion years after the Big Bang. And that's hard to do because now you need many generations of stars to go through and you have your work cut out for you. Suppose that in fact it's the redshift 5 galaxy, which has its star formation quenched. That doesn't work either. How do you turn off star formation? Not age is the usual way, but it's not that old, so you can't turn it off by age. You turn it off with the environment. No matter what redshift it is, it's going to challenge galaxy evolution models and create problems. So there you are, JWST and Schrodinger's galaxy are creating problems. We are used to seeing gravitationally lensed images of galaxies. And in this image, the very thin red curve that runs diagonally through the image, called the sunrise arc, is in fact a lensed galaxy with a redshift just over 6, roughly 12.8 billion light years away. Actually discovered by the Hubble Space Telescope, but observed by JWST. And the 4 little dots that you see up in the upper right labeled Arundel are 4 images of what appears to be an individual star, which makes this by far the first high redshift image, not of just a galaxy, but an individual star, which is really pretty impressive. The star, the photometric data for the star, which is the little squares and the little black dots with vertical error bars, uncertainty limits, fit very nicely a luminous blue variable, which would be a supermassive star or a B-class star with a high temperature around 15,000 kelvins. It looks like one of these stars. You could, as the plot on the right shows, make it a binary, and that produces a good fit too. But once you allow it to be a binary, there's of course a very large number of pairs of spectra that could combine to give you a good fit to the photometric data. So this probably is one star, but we will have to wait to see. Maybe we can get good spectroscopy, but it's very difficult to get spectroscopy just on that star. The galaxy, perhaps, yes, but the star, that's going to be a problem. So when we're ever going to find out just exactly what Earendel really is, remains to be seen. But I find it quite fascinating that we can actually see the high redshift image of one single individual star. Star formation is one of the science goals. And this is an object that I've actually looked at before. The last task I worked on when I was at JPL was the Spitzer Space Telescope, before I retired in 1908, in 2008. I'm not that old. I went back in 2013, 2014 to work on, as a contractor, on high resolution images of protostars. And this is one of them that we looked at, IRAS 15398, which we figure is about 2,400 years old, about 500 light years away, very nearby. And what we were doing was making a catalog of protostars, but we analyzed a number of them to figure out if there's a correlation between the age and the opening angle of a protostar jet. And we did. We came up with something, and our plot demonstrated that there is a bifurcation, basically two different relationships, depending on whether your protostar is more or less than 8,000 years old. And this is considerably less than 8,000. So I just do this to show you that this is an object we've looked at before. And besides, I like to show off my own papers now and then if I get a chance. And so this object was looked at with the MIRI spectrometer. And the basic problem they're looking at is that young protostars have complex organic molecules in them. And how do they form? The star doesn't have the molecules in it, the cloud around it does. And how do they form? Up until now, we've only been able to detect the gas phase for these molecules, but they require surface chemistry, ice grains in particular, in order to form at all. And there's a great deal of interesting chemistry that goes on, even at extremely low temperatures. So this is the imagery they come up with, which is a lot better than the cheap image you saw a minute ago that I cropped out of our paper. The image over on the far right is an IRAC image from Spitzer, which is heavily pixelated. Spitzer is a very small telescope with an aperture less than 1 meter, 85 centimeters, whereas the 6 meter JWST can get much better images, which you see the three on the left at 5.6, 7.7, and 10 microns. See the typical double lobe structure. There's a bright source on the upper left and the lower right. The source itself, the protostar itself, is actually in the middle somewhere. This is an axial jet plowing in to the material ahead of it, which is why it shows up as bright spots. But the real show for this object is the spectrum that comes out of the MIRI MRS. This is a really great example of what spectroscopy does for you. The wavelength plotted along the horizontal goes all the way out to 28 microns. The complex organic molecule region is this red curve over on the left above the spectral lines. And it's expanded in the box on the right, so we can see features identified with various molecules and some that are unknown. And in the spectrum itself, under that, we see CO2 features, ammonia is NH3, methane is CH4, water, there's water everywhere in the universe, and others, the chemical formulas. I'm not a chemist, so I can't tell you exactly what those are. But this is a really good picture of the chemistry that's going on inside a protostar, the area around it, or really any nebulous object, any nebula. You see silicates, you see water. The plot on the bottom is just a difference between the spectrum that you see and the dashed line above it, which would be basically thermal emission. If there was nothing there, you would just see temperature. And the difference between them is what you see plotted on the bottom. But the really interesting plot, to me at least, is the one up on top, which shows very well what's going on. And I'll note that the Spitzer spectra of this object, which are the yellow lines, don't go as deep as the blue spectra from JWST, which shows you the lack of sensitivity for the small aperture of the Spitzer Space Telescope. It had good detectors on it, but it was little, so it could only get so much light, whereas the 6-meter JWST gets a lot more light and gives you a much better and much truer shape to the spectrum, and could arguably change your thoughts about the physics of what it is you're seeing. Now, exoplanets. This exoplanet, let's see, I can't read the number because, oh, there it is, HIP. HIP is Hipparcos catalog 65426b. What we're doing here is taking a direct image of an exoplanet, and this is the first direct detection of an exoplanet obtained by James Webb, and the first direct detection obtained by anyone at a wavelength beyond 5 microns. And here's the nice picture. This is a MIRI, and it's doing coronography. So a black disk called a Lyot stop is placed in the optical train that blocks the image, physically blocks the image of the star. So that most of the starlight is blocked. That enhances the contrast and allows you to derive an image of the exoplanet, which is what you're seeing. The bright splotch is the planet. And on the two images on the left at the 3 and 4.4 microns, you notice looks like 3 instead of 1. Well, that's just an artifact of the instrument. What's this image? Let me go back for a minute. This image is one that's made to be put on a web page, put in the image gallery for public consumption. And you could easily make the mistake of thinking, I just put a coronagraph in there and voila, look what I see. This looks fantastic. That's not what you see. The two images on the left here are what you actually get out of the telescope. You still have to do an image point spread function subtraction in order to derive an image of the exoplanet, which is lost in the glare in the image on the left. But because the Lyot stop has blocked out most of the light of the star, you can do it with more fidelity and actually cover the planet, which you could not do probably if you did not have the coronagraph stop in the way. And there are different ways of doing that that are labeled ADI and RDI here. And here are two examples, the 3.56 and the 11.4 micron channels, where you can see that the results of that image subtraction. And on the upper images, the little ring of dots around the planet. There's 1, 2, 3, 4, 5, 6 bright lobes around the planet, are part of the point spread function of the telescope. It's what you would expect. And as I've highlighted in blue at the bottom, we note that the distinct hamburger-shaped central core and 6-lobed structure of the companion PSF in the NIRCam images is an expected feature that is related to the layout stop design and not indicative of discrete astrophysical source. So you still have to do a lot of work, but you can indeed directly image extrasolar planets with JWST, and they will be doing a lot of that in the future. Now, what I've got here amounts to a few pretty pictures with not too much science to say, but they're interesting and worth looking at. This is an image of M74. The Hubble image on the right is optical, mostly optical, and James Webb image on Hubble image on the left, excuse me, and the Webb image on the right is infrared, and combine them both to get in the middle. But if you look, the infrared image on the right is completely insensitive to stars. So most of them you just don't see at all. The optical image from Hubble on the left is, of course, very sensitive to stars. So you see a typical great grand design spiral galaxy like you're used to seeing, with the nice dust lanes and the red H2 regions. But over on the right, you're only seeing the dust, some line emission from gas. For instance, some of the star formation regions, like here in the upper left, on the left plot of the Hubble, you see star formation regions that glowing pink for hydrogen alpha glow. You see them here in the infrared, and this is going to be a combination of heated up dust that you're seeing in the infrared and hydrogen alpha. Now, what I find fascinating is if you look towards the bottom of the Webb image, bottom left, there is a very conspicuous, really black splotch that doesn't match any of the other dark spots in that same image. All the other dark spots have something in them. They don't look as dark, but this one looks ridiculously dark. If you look at the Hubble image, there's nothing peculiar about that spot, and you just never notice it. So I have no idea why that looks so different, but I surely would like to know, and I think maybe that's something we need to follow up. But here you can see a very good example of the difference between infrared and optical imagery. Here is a recent released image from NIRCam of the Tarantula Nebula, which I think is in the Large Magellanic Cloud, about 160,000 light years away. A really nice image. The orange-red colors that dominate the upper left of the image indicate hydrocarbons, molecular clouds. The star cluster stands out very nicely at the center of the image. The short wavelength images, like especially shorter of say 3.6 microns, are going to be dominated by starlight. So a star cluster like this will show up very easily in short wavelength infrared. However, if we compare these images, this is the MIRI image on the right, long wavelength, and the NIRCam image on the left, the entire star cluster disappears completely. And in fact, lots of the background stars you see over on the left image are gone. This great big dark region on the lower left of the MIRI image on the right is almost devoid of anything because the starlight doesn't figure at those long wavelengths, except for the one very bright foreground star that pumps out so much that even at long wavelengths, you're going to see it. But unless it's a really bright star, you won't see it. But you do see that, for instance, the dust clouds, hydrocarbon clouds perhaps, that stick out into the star cluster on the near cam image are glowing blue, which means they show up in short wavelengths on the mirror image. And the dust stands out much nicer in the long wavelengths. But this is a neat trick. We can make entire star clusters disappear just by changing the wavelength we view at. And I've seen X-ray and ultraviolet images of M51, the Whirlpool galaxy, where the entire dwarf companion galaxy vanishes just because you've chosen a wavelength that is not sensitive to the starlight that characterizes it. I trust you all know what this is without me having to tell you. The solar system was not listed on the science goals of the of the James Webb Space Telescope, but it's clear from this image that observing solar system objects is something that will work out very nicely for James Webb. It has a nice big 6-meter mirror. Remember, these are fake colors. This is all infrared, so none of this is visible and real, but you get a lot of nice detail around the red spot, especially the rotation of the clouds, which doesn't always stand out as well in Hubble Space Telescope images. And if we zoom out, now we're seeing aurora, and the southern aurora is so bright that it creates a diffraction spike in the image. I'm a little surprised at that. I would not have expected the aurora to be this bright in infrared wavelengths. So I'm surprised and happy to see that it is. I'm sure that tells aurora people something. You can see the rings of Jupiter. Right under the word rings, there's a little white bow off to the left. The moon at Astra, the moon Amalthea. Io is out of the picture over on the left, but it's so bright, it's creating a diffraction spike as well. And I believe Rhea is over like on the right. I can't see what's covered up by the talking heads of Zoom. And with that, I'm done, and I'll sit here and answer questions, and for as long as it takes. So,
Tim, thank you very much. It was, as usual, wonderful, informative, partly over my head.
Tim, one question I've got is,
yeah,
and you may have answered this, I had to step away for a moment and come back, but do you know when they plan to do a true spectroscopic redshift measurements versus the photometric redshift measurements they're doing right now?
Well, if you mean for like the Schrodinger's galaxy, that will be done in September.
Okay.
Not September, excuse me, December. They're going to do that in December. So they're doing photometric redshifts and spectroscopic redshifts all simultaneously. They just haven't got around to doing a spectroscopic redshift for that object yet, but they plan to do it in December and nail down for sure whether it's actually a close redshift or far redshift.
Okay.
Well, I asked a question. I don't see it in the chat anymore, but I'm going to ask it now, Tim. The JWST-8.
Somebody has some background TV on or something. Can you check
I don't.
that?
It's not me. I don't know who it is.
Thank you.
The JWST-8 dozens, maybe more, scientific projects, maybe more. And it's proven to be a very, so far, successful project. My question is simply asking a professional astronomer, do you think it was worth it, or is there I'm not a big JWST fan, as you can tell, because I have many people at both JPL and others whose projects were canceled because of budget problems. So I'm just asking, do you think it's, I guess, do you think it's worth it?
Um,
And I know that's a tough question and subjective.
It probably is, to the extent that the James Webb Space Telescope will be able to see and do things that, to the best of my knowledge, none of the other competing science projects would have been able to do. We clearly would have learned a lot from projects that were canceled because of the budgetary pressure created by JWST, but none of those projects would have been able to do what JWST is doing, and that is to focus on the extremely early universe. Will we actually see the first stars and the first galaxies? If we do, and it looks like we have a good shot at seeing that, then I think it will be worth it, because we will have opened up huge new areas of research that people can get into. And since there is no equivalent of JWST at the moment eating up all the budget, there will be an opportunity for more projects to work on these very high redshift objects.
Thank you.
Tim,
Yeah.
I've got a telescope question.
Yeah.
So everyone here, I think I could say, probably has a telescope. I just read my Sky Telescope, which arrived today, and on a couple of the images you showed, one was a hexagonal pattern on the planet, and then in the main one there was the 6 spokes in the diffraction pattern of the stars. And it was explained a little bit in the Sky Telescope, but I wanted to ask you about the mirror configuration on the JSWT, why those are there and why they're different in my job.
Let me go back.
Yeah, the main image with the, and then there's an 8th bar that the Sky Telescope said was one of the arms supporting it, but it's supposed to be, I was kind of curious whether is it because each mirror is a hex, or is it because the whole mirror, all of them together, is kind of hexagonal, or what's the story? How does that work?
I don't think you're seeing anything that has to do with the hexagonal shape of the mirror. The spacing and the joints between the mirror segments does create a visible artifact in the point spread function, but it's extremely small and probably not noticeable. The diffraction spikes certainly caused by the long arms that are holding up the secondary mirror. Why the diffraction spikes come in the pattern they do, and I'm not sure what, like here you have 6 spikes, but there are 3 arms.
So that bright star there's a good example, right? So what the article said was, there's another good example, that the hexagonal pattern had something to do with how the mirrors are set up. And then that vertical bar across the middle, the horizontal one.
Oh yeah, you can barely see it here, but it's there.
You barely see it, but it's there. And they said that was something to do with the arms, but I didn't quite understand.
I think Tim, if you could allow me to, I think the main dominant thing is the outer envelope of the mirrors, not the individual hex segments, but that outer envelope. It's not circular. And so you're going to get diffraction spikes from that. If you kind of just imagine a straight line along each of those edges, you got
that was kind of my question. Was it the overall hexagonal shape, or
from the analysis? I'm retired now. The software that I used to work on was used for designing this thing, or at least analyzing it. And the main dominant diffraction is from those edges. There's a little bit of diffraction from the individual segments, those gaps are so small, it's really minor. And there's a little bit of diffraction from the truss support for the secondary. That's pretty minor. The main dominant diffraction for this telescope is from, if you just kind of sort of draw a straight line to sort of connect the dots along the outer perimeter, that is what's really doing the main diffraction based on the software analysis that I've seen.
Tim, if you
Hello?
if you mind, another question.
Yeah, Jack here. I was just going to say that it's the seams between the hexagonal facets. All those lines are the, between all. Think of it as a spider with numerous veins in it, and the hexagonal shape is what gives you the 6 spikes.
Yeah.
Tim, what so far has been, and maybe you answered this, I don't recall now. What's been the most aha, that's amazing moment so far? It's been very few weeks or months, but what has really gotten your I don't know, just made you very, very proud, or not proud, just amazed or thankful, or just, this is awesome?
For me, the most amazing part of the whole mission, excuse me,
other than it unfolding.
Well, yeah, the fact that it unfolded is pretty dang amazing all by itself. But it's the search for the high redshift, really high redshift galaxies and the first star. So something like a redshift 17 galaxy, if that plays out, and there are several other candidates for redshifts that high. Excuse me. That will be the most exciting part of the mission to me.
Thank you. Cut back on that rum.
I had
Trust
a quick
me,
question.
if it was rum, the talk would have been a lot more interesting.
Well, thanks again, Tim. Should probably give Tim his round of applause, and we'll get to the.
Thank you, Tim. Amazing as usual.
You're welcome.
Thank you, Tim.
Fantastic. Thank you.
Yeah.
Remember, this is all reviewable on YouTube. You can go back and get that. What did he say?
Yeah, that happens to me all the time.
So Spencer, do we want to start? We'll give everyone the last minute, get your.
Yeah, I just reposted the link for the drawing, so I'll close it out. I'll give everybody about maybe 30 seconds or so to get there.
Daryl, there was a text from, or a chat from a new member that joined late, so you might want to say hi and tell them to enter the drawing.
Okay, I was just entering the drawing myself.
Well,
I'm sorry, go ahead and point that out. Go ahead. Who is it? Greg?
Meg Young Chung.
That's it. Yeah.
Yeah. Go ahead. There's a link for the door prizes right at the bottom of the chat, or pretty close to it. You click on that, open up your web browser and type in your name and email address. Who knows? It's a random drawing. It's supposed to be random drawing. I don't know what kind of tricks Spencer's pulling back there in the software, but
you notice I have not entered the drawing.
Actually, they're using quantum entanglement, so it may not be quite random.
Okay, so that should give everyone time.
Yeah. All right.
Let's close that out.
Close it out.
Yeah, let's close that out.
Hey, Tim, a quick question.
Yeah.
Not related, not really related. I was just curious, how far does the Chara go out as the deepest space objects that it can reach?
Chara array, the interferometer at Mount Wilson, has not yet looked at any deep space objects. It looks only at stars in the Milky Way. However, there are plans to use it to observe active galactic nuclei. They have, I think, already actually done some observations which they haven't told anybody about, won't tell me about. I know that won't, because I asked them and I punched them around and they still won't tell me. So I know that they've looked at some.
Can you
AGN.
quickly summarize what Chara is?
Chara is an optical interferometer of 6 telescopes at Mount Wilson Observatory. It has a maximum baseline at the moment of 330 meters, which makes it the largest in the world, largest and most capable. Chara is an acronym, stands for Center for High Angular Resolution Astronomy of Georgia State University. They do most of their observing in near infrared, 1 or 2 microns, and some in the visible, but mostly near infrared, where light pollution does not exist, and therefore they do just fine. It is, at the moment, as I said, the largest in the world. However, they have received a grant for a 7th telescope, which is under construction, will be portable, and we're negotiating spots to move it around on the observatory grounds now. That will give it a 1 kilometer baseline. They're putting adaptive optics on the telescopes and on the light bench where they combine the beams. So they should have the capability to actually make meaningful observations of active galactic nuclei sometime in the future. Their problem is they have 1 meter aperture telescopes, and so they're limited in how dim they can go.
Tim, I have a question about the mobility. If it's mobile, would you have to build a light pipe from wherever you decide to put it?
They're going to use fiber optics.
Oh.
And all of the telescopes will eventually be using fiber optics instead of the evacuated beams that we have now. And the guys on the mountain built a trailer that mimics the new telescope and drove it around the observatory grounds to make sure that it will actually get to the places where we want to put it. The road's not too narrow, that there's enough room between the things on the side of the road.
So the grounds are big enough.
Yeah.
Tim, if you don't know the answer, who would I talk to? How do you maintain coherence with fiber optics?
That I don't know, because I know a lot less about optics than you do. But the optics people at Chara insist they can do that, and they've probably already demonstrated that they can.
Is there someone I could talk to? I'd love to understand this, because this is really cool.
Norm Vargas.
Probably Norm is a good person to start with.
All right,
Good start.
thank you.
Okay, I'm
So,
ready
but
ready
fiber
for-
optics, I always think of as being very small, and I know that the light beam that comes down the light pipe is pretty big. It's like
it's a 5-inch beam, but I suspect you can compress it without too much trouble.
I see. Okay.
Okay,
All
I'm
right.
ready to start the drawing.
Okay, cool. Let's do that then. Thank you, everybody.
All right. So first winner, who's recording the names? Alicia, are you?
We don't see the names yet.
Oh, you don't?
We don't.
Oh, okay. Hang on.
Still Tim? Do you have to let go, Tim? There we go.
I have to let go.
All
Yeah.
right. So the first one is Richard.
Is Alicia there? But I haven't heard her.
Alicia is here.
I'm working. Hi.
Okay.
Yay.
Okay, so that's Richard, and I'm gonna...
What did Richard win?
Oh, he won an Amazon gift card.
Uh-huh.
Okay.
Cool.
All right.
Buy
Next
another
one
camera.
is Greg Thompson.
Hey, Greg.
Woohoo. Yay.
He won a LAS hat.
My first one.
All right.
So tiny. Let me see.
All right. Next one is Mike Gardner.
He won a laser.
All right.
All right, thank you.
Kevin Gilchrist.
Oh, for real. He won a celestial observer's map of the moon.
Okay. And Stephen Gaffney.
A new member.
Yay.
Look at that, I won something on my first day.
Hey,
There you
jump
go,
in.
Stephen. All right. What did Stephen
Yeah.
win?
He
It's
won
always a great start.
red flashlight.
Red
It's just what you need.
Right.
Yeah.
Oh,
Good
exactly
start.
what I need. Awesome, thank you.
You never have too many.
Nope.
All right, Teresa.
Oh, now I can see it. She won a gift from the LA store.
Store.
All right.
Hey.
Cool.
How many more we got?
That was the last one.
Okay, all right.
All right, thank you.
Thank you. Cool.
That was it? Okay. All right, so we did the last one. All right. Okay, well, everybody, the new members, go to Garvey. It's a good spot. We could probably end the recording and then everyone can chat.
Tim, thank you so much.
Oh, you're welcome.
Yes,
All right,
thank
I'm
you.
stopping